mean free path. So gas particles go in a straight line till they run into something. The average distance that they can travel without colliding with something, either another gas particle or the sides of the container, is called the mean free path. So free path, how far can you go without running into things? Mean is the average. So the mean free path will decrease as the pressure increases. So as the pressure increases, you can imagine it's more crowded in there, and so they're going to run into stuff sooner. Just for an example of how long this path is, if nitrogen was the size of a golf ball, it would travel about 40 feet between collisions. That's actually quite a long distance. So this is illustrating in a box. Here we've got this particle, and it's moving around. It bumps here, it hits there and there and there. Reminds me of the Family Circle cartoon where the kid is going all over the place, right? If you took the length of each of these line segments, the mean free path would be the average of those. So here's two new words. It's new to the class: diffusion and effusion. Very similar, but not the same. Diffusion is the process by which gas molecules spread out from a high concentration to a low concentration. Heavier particles diffuse more slowly because heavier particles have slower velocities.
And the mean free path, it would increase if the volume increased?
Yes, if the volume of the gas increased at the same temperature, then the mean free path would increase. And the mean free path is going to be related to the pressure. The pressure would go down. So diffusion. So we are all familiar with an example of gas diffusion. So imagine my 11-year-old in the corner, and he ate too many beans yesterday. And he lets one, right? Big old fart in the corner. Stinky. If I'm over here on the other side of the room, am I going to smell that immediately? No. But is it going to get here? Yeah, it is. Because what came out is a gas, and gases spread out. They diffuse from high concentration to low concentration until it's the same throughout. So that's diffusion. Effusion is when a gas escapes through a small hole into a vacuum. Kind of weird. We'll look at a picture in a minute. The rates of diffusion and effusion are both related to the root mean square velocity. At the same temperature, the rate of gas movement is inversely proportional to the square root of its molar mass. So at the same temperature, heavy particles move more slowly. They are going to diffuse and effuse more slowly. Small particles move more quickly. They will diffuse and effuse more quickly. And the book goes through derivations of this as well, so if you're interested, I encourage you to go through those. So this is illustrating effusion. So we have a box here with two sides. They're divided. On this side initially there were no gas particles, a perfect vacuum, nothing in there. There's a little tiny hole here, and we have a gas over here. This gas is going to have a pressure. Over here, there's no gas, there's no pressure. So I don't know about you, but what my mind naturally thinks is that this is a vacuum. It's sucking the particles out of this container, right? Because vacuums suck things in, right? So it's sucking the particles out, and they're going to go whoosh, and they're all going to run out. That's not what's happening. The vacuum over here is nothing, and it's sitting there doing nothing. The particles over here are behaving just like they would if there wasn't a hole in the wall. They're going to be zinging around, bouncing into things. But there is a hole. And occasionally, one of these particles in its path will hit that hole head on and go straight through. It's not being sucked in. It's just going on its merry way, and it happened to hit the hole in the wall. It goes over here, and it continues to bounce around. Now, at this point, I have 3 molecules over here. Are any of those going to hit that hole? They might possibly, but the probability is much smaller because there's only 3 particles here, and there's a bunch here. So these particles are probably going to stay on this side of the container. These particles are going to continue to bounce around, and occasionally one will hit the hole and go through. That is effusion. The rate of effusion is related to how fast these things are moving, right? Because if these are moving around like maniacs, more of them are going to get through that hole. And if they're moving very slowly, it's going to take a lot longer before anybody hits the hole straight on. So we can look at the relative rates of effusion for 2 gases. The rate of effusion of gas A to gas B is equal to the square root of the ratio of their molar masses, but inverted. So rate A on the top, molar mass A on the bottom. Rate B on the bottom, molar mass B on the top. Because the heavy gases are moving more slowly, the rate of the heavy gas will be slow. Yeah?
So for the example, if you like poke a tiny hole in the balloon, like the air around the balloon, it's considered a balloon.
That's a good question. So what about this balloon thing? So helium escapes from the balloon faster than air because the helium atoms are smaller and thus they're moving faster, and so they effuse faster. So going from inside a balloon to atmospheric pressure outside is not exactly effusion because it's not going into a vacuum, but relatively speaking, it is. The thing about balloons, though, is that the balloon volume can change, right? And so the pressure being exerted there gets a little bit wobbly. It changes. And so you're going to have a different experience than if you were looking at a box with a rigid size. But you could do an experiment where you have 2 balloons, same kind of balloon, obviously. Fill one up with helium and one up with air, so they're the same size. Tie them off and wait a couple of days. See what happens. The helium balloon will shrink faster than the balloon filled with air. Not because the particles of the air cannot get through the latex balloon, but because the particles of the air are much bigger, and so they're moving more slowly. And so it takes them longer to hit one of the little holes head on. It's really kind of trippy to think about. You think about latex balloon, it holds air in, the air can't get through, right? No, there's lots of little holes in the latex and the air can get through, it just takes a long time. So we don't notice, right? But it'll get through eventually. Mylar has much fewer holes, and so the Mylar balloon will stay for a long, long time. So that's Graham's law of effusion. Find the ratio of the diffusion rate of hydrogen gas to that of krypton gas. There will be a question like this on the exam, and there probably will be one about diffusion and effusion on the final exam as well. But this is not a big deal like stoichiometry, molar masses, those sorts of things are a big deal. This is a little deal. So here, rate of effusion of hydrogen to krypton. We're going to use the law of effusion, which is, instead of A and B, I'm going to use the element symbols. So the rate of hydrogen to the rate of krypton. And I put hydrogen on top and krypton on the bottom because it says the ratio of this to that. So I want hydrogen to krypton. And this is equal to their molar masses, square root ratio. But it's an inverse relationship. So the rate of hydrogen is on top, the molar mass of hydrogen is on the bottom, the rate of krypton is on the bottom, the molar mass is on the top.
Is this mass in kilograms?
It's an excellent question. Is this mass in kilograms? Technically it is, kilograms per mole. But the thing is, because we're looking at the ratio, it cancels out. So if you use grams per mole in this equation, it works just fine. So the molar mass of krypton is 83.80 grams per mole, and hydrogen 2.016 grams per mole. The units cancel out. It ends up being a ratio. If we did this with kilograms, it would be 0.08380 kilograms per mole divided by 0.002016 kilograms per mole. And you end up with the same answer. .447. So this is saying that hydrogen gas effuses 6.447 times faster than krypton. .447 to 1. Any questions?
If hydrogen was on top and krypton was on bottom, then we were looking for krypton to hydrogen?
Yeah, then we'd be looking at the ratio of krypton to hydrogen. And usually when we have ratios, we want the thing with the higher value first and the smaller value second, so that we get a ratio of like 3 to 1 instead of a ratio of 1 to 0.33, which is harder to think about. So root mean square velocity problems, Graham's law of effusion problems on the exam are going to be pretty straightforward. I'm not going to try to trick you or do fancy stuff. It's like, can you use the equation? Do you know what the letters mean? Now the stoichiometry problems, there'll be tricks and all kinds of weird things thrown in there. But this one, just use the equation, be okay.